Okay, sorry to switch back. So let me repeat. Oh, okay. So Bernoulli, let me repeat. Bernoulli actually we care about what you want or what you don't want, or equal success or fails. All right. And so the other, I think you can derive. So double check comment. Comment for Bernoulli. Here we have the experiment associated with fails or succeeds. Okay, so this is sometimes called a Bernoulli trial. If we can extend Bernoulli trial to fixed number of trials and want to get number of success, and this way we can have a binomial. Or maybe we don't have the fixed number of trials until we have the first success and the number of failures before the first success. Then we can have the geometric distribution. Okay, so this is a way to have the two stories, binomial and geometric. And that's all. So this is the simplest one, Bernoulli. So Bernoulli actually, where to apply Bernoulli? If you want to use it to have the two random occurrence, one you want and one you don't want, or simply one success and one failure, and then you can use Bernoulli. Okay, that's it. So this is Bernoulli. All right, so Bernoulli, okay. All right, so I think, okay, previously you guys have the reminder by calling me. So I think I changed the mode. And next one, discrete uniform. This is a discrete uniform. Okay, so we have an integer I to j. All right, so how many is this one? So each one has the same probability. So that's why j minus I plus 1. This is the total number of the points. All the points share the same probability. So 1 over the points to indicate the probability shared by each point. So these, I think you guys can check it. Likewise, these can be checked. And for these, same as the continuous random, same as the continuous uniform. So we have the minimal and maximal value. As a common, it says this, discrete uniform equal to Bernoulli if Bernoulli with a half p equal to a half. This one. Same. So you will have the uniform. Actually, for Bernoulli, we associate with the number 0 and 1. So that's why common one will be okay for these. So this is discrete uniform, and that's all. So about the second distribution, is it okay? Discrete uniform. All right, so if it is okay, then we check binomial. Binomial using the story of Bernoulli trials, number of successes, right? So this is the first application. Or maybe simply it is called a batch number. All right, so if we want to describe Bernoulli, actually follow the probability density function. And this is a binomial coefficient with the calculation, right? Why? Because we try t times. Among the t times, perhaps we choose x success. T minus x fails. So x success, you will have a p raised to the power to x. Fails the same, 1 minus p raised to the power to t minus x. And also multiply the coefficient. Finally, you will have the PMF. Okay, so likewise, you can try the others. Well, about mean, I think mean you may have the special derivation. Perhaps you need to use differentiation. I just remind you of these, and I think you can check it. Differentiation associated with the derivation to get mean. All right, so for the others, I think that's all. All right, so let me check the comments. First one, it is a story. Story between Bernoulli and binomials, I think it's really direct. And second one, I think you can try Doberman-4. Then we have the useful results. And the 3, I think it's really trivial. And this one you can try by using Supplement-1, and the same, it's really trivial. Why is trivial for item 4? Item 4, previously, we want to get the number of success. If you use t minus x, that means number of fails. So of course, we can switch the associated probability from p to 1 minus p because of fails. And also, if we only have one for the trials, and then of course this one will turns to be Bernoulli. Okay, so here this is a binomial. All right, and that's it. So is it okay? If it is okay, next one we want to check geometry. Number of failure, I think you got it. Oh, maybe the others, demand size or the batch size. Okay, and follow the previous story. We have these. Number of fails. So number of fails and then success. But sometimes we can have a geometry, including success. So including success, then we will have the form. -1. And the range, including success. So from 1 to the others. So this one also called geometry. This one or this one. So you can call this is a geometric one. And this is called geometry 2. And that's all. As for the others, I think left to you, so I do not check in detail. And about the comments, this is a story. Okay, so I think you can check the story. And this one, you can check supplement 4 by noting that geometry is a special case of a negative binomial. And this one, I think it's really easy. You can understand that. And this one, if you want to relate geometry to a negative binomial, so when it is a special case of a negative binomial, when negative binomial with the first parameter set to 1. Okay, so this is a story for geometry. And this is a discrete case of exponential, right? Okay, so up to now, that's it. So the same, you can think about if you have any question, let me know your question within 2 minutes, because I go through the distribution quickly. But I think if you understand the idea behind checking the distribution, I think it will be easier, because you may rely on the supplements, or maybe you may have some idea to have some explanation on the selected distribution. So let me stop here for 2 minutes. If any question, you just let me know. So if any question, you can let me have the questions through message, or maybe you can call me directly. Check it. So any question? Well, I think maybe no question. So I just follow the previous story to check the next story. Negative binomial. Negative binomial similar to geometry, but try to extend geometry. How to extend geometry? For geometry, right now, we have failure, and success. And then you can try next one, success. So you can specify number of success, for example, S. And exactly it's S. So you see, we may have the story, number of failure before X success. Okay, the X success. We try the independent Bernoulli trials. Okay, but this one is excluding the number of success. And then if we have S denote number of fails, and you should plus success S, right? So if we have this, you see, to the final S, success. So final X is fixed, right? So if we use S plus X minus 1 minus the fixed one, for the others, where you have for the ferrule not fixed, so you can choose X position. Choose X position to be failure, so you have a failure. As for the remaining, you should have P success, so it should be S minus 1, but the final fix you should multiply. So that's why you have this PMF. According to my current explanation on the probability density probability mass function, is it okay for you guys? S plus X minus 1 minus the fixed one, and then choose among the number to choose X, so X failures, right? And collect the probability, but don't forget to append the final success. So still have a P raised to the power to S. Even initially you minus the fixed one. Okay, so this is a story why we have the PMF for the negative binomial, and also we have the story to let you know how to define the negative binomial. Okay. The same for the others, I think you guys can check it. So I go through that quickly. And this is a story. Okay, story says geometry. So get some geometry, geometry, geometry. Why some follows this story? It's really simple. Try to count first one, second one, S1. So of course it count the whole story. So finally the whole story is the negative binomial, right? So I think this one you can understand. Or you can use the idea. This is a negative binomial, negative neg bin 1 and P. So get a sum, you simply collect the parameter. So of course you have an S directly. So you can use that way as well. So common one, you can use the story to explain, or you can use supplement 4 to explain. Okay, so this is common one. And common 2 says if we have a Bernoulli, and in fact, this is a story. This story. So you can follow this story to have the results too. So I think you can check it. And item 3, I think this is supplement 4 directly. So I skip it. And 4 actually says the special case. So the same, I think it's simple. I skip it as well. And that's all. So right now, this is a negative binomial. So negative binomial, you guys need to focus on the story here. And then I think you can understand. The same, this is the story excluding success. You may have another case including success, so that no need to exclude. Is it okay? So another version, I think you can look up the other task force to have another version of negative binomial. And that's all. If you want to try the story similar to this, you can try. Once you have the PMF for the second version of negative binomial, I think you can check with the other task book or check with the other possible reference book, and then I think you can fully understand how to extend to another version of negative binomial. And that's it. Okay, this is negative binomial. So up to now, let me have a summarize. You can have a Bernoulli, binomial, geometry, negative binomial. So how about this? Negative binomial is a special case. A binomial is a special case of a negative binomial? No. This one. Okay, and this one. Bernoulli will be a special case of binomial. Geometry will be a special case of a negative binomial. As for the others, can we cover some of them? No. All right, so they are separated unless geometry be a special case of the negative binomial, Bernoulli be a special case of a binomial. And that's it. So you can check the story, and then I think you can have the story clear, and so that you won't mix them up. Okay, that's it. So this is the current discussion for Bernoulli, binomial, geometry, and negative binomial. Is it okay? If it is okay, and next one, it is a counting number of events. So counting how to count this way. Okay, and this way, lambda here, we will have 1 over beta. So the same. So usually we have the convention. Lambda serves rate. Beta serves the mean duration. So that's why we have this relationship. Lambda equal to 1 over beta. Okay, if we specifically employ lambda, we intend to use lambda to denote rate. And the beta usually we use to denote the duration, in particular the mean duration. All right, so number of events. So actually you can use number of batch size. So if you want to count the batch size from 0 to to infinity, then you need to use Poisson. Poisson with a special property, same mean and variance. It doesn't mean same mean and variance. It means mean equal to its variance, and that's it. All right, so that's all. And about this, it says Poisson actually from Poisson process. Poisson process means inter-arrival time exponential. But we have a Poisson process. Poisson process, you will have a t. But how to make it to a Poisson distribution? T equal to 1. And then you will have a story 1. Uncommon 1. So you guys can check it. And I think in our supplement, I forgot which supplement, but at least one of the supplements says the merging property. So that's why merging property still be the Poisson, but we have the aggregated rates. That's all. So this is Poisson. Well, up to now, is it okay? Perhaps I go through this quickly with the help of supplement. So I still emphasize you guys need to go through the supplement to know more from supplements, and so that you can understand more for the current discussion for chapter 4. Is it okay? Maybe this time, I mean, before discussion, chapter 6, perhaps you are still, I mean, you are not still familiar with the supplements, but I think once you want to reach chapter 6, you need to understand the details of supplements, including chapter 4. So I think it's still okay. You guys can check all details in chapter 4 and the supplement for chapter 4. Once you understand, I think you can understand the current discussion. And these are try to have the mapping to some of the supplement with the proper numbering. Maybe some of them I failed to let you know. For example, about the person. Okay, I forgot which number of a supplement, but I think you can check it. And that's it. So checking continuous or discrete distributions, we need to rely on the supplements. So be sure you are familiar with the results of a supplement, and so that you can fully utilize the results there to help you understand the current comments. And that's it. Of course, some of them beyond the supplement, maybe sometimes, but I think still acceptable if you can understand some of the other concepts to have the further derivation or the further explanation. And that's it. These are the continuous distributions and discrete distributions. And next one, it is called the empirical distribution. Okay, so how to form the empirical distribution? Here, we assume we have 6 points. For 6 points, checking the interval, 6 minus 1, we have a 5 interval. Why 5 interval? Because we want to use 5 interval to share the probability. The first one with 0 and the final one with 1. 0 and 1. The intermediate one with 5. So each one share the same probability, and that's all. So we try to construct CDF directly. Why CDF directly? If we want to generate some of a variable, in fact, we care about CDF rather than PDF. So we generate CDF directly. So in this way, we can have the way to construct the empirical distribution if we simply treat them be the equal point and use the inner point to, the interval. Use the interval to share the probability, then we can construct the CDF. Okay, that's it. This is the first version. If we have the first version, I think you guys can try to use the linear interpolation. Linear interpolation. To find the line segment so that you will understand the line segment. As for the line segment, I think at this moment I skip to the right. You guys can try. Is it true? So you can use linear interpolation and so that you can have the line segment. Why line segment? Because no choice. We use line segment to have the CDF. For the previous one, look at these. Available but not grouped. Okay, so currently no grouping. So we have the individual point from the data. Another one with a grouping. So group data. Okay. For example, we have this one, 1, 2 to K. Right? So we have a K interval. And for the K interval, we have the individual counts and the total count. So right now we do not have the same one, but we still have the same one for individual, so that we can have the proportion, and proportion, finally to the final one. So the proportion for the first interval, add the proportion of the second interval, etc. So you can have the arrangement if we have the proper proportion. And likewise, you can define the function g of aj by defining if a0 equal to 0. Then you will have the linear the line segment. The same using the linear interpolation, because we have the proper grouping. So you should use these, and so that we use the endpoints for the group. And that's all. All right. So for the derivation, I skip it. You guys can try. All right. And actually, some of the exercise can ask you try, but I skip the way to let you try. I think that's all. We finished the discussion for that. For three possible distribution: continuous, discrete, and empirical. All right, empirical here, we don't care about discrete or continuous or not, because we model it to continuous, right? Because this is a continuous function, so of course we model to the something like the continuous, but it doesn't mean continuous. So let me tag it back. CDF without discrete or continuous for the empirical distribution. All right, that's all. This is the discussion for today's classes. And any question for you guys? If no, that's all. And I post the second programming assignment as well, right? So the same, I allow you guys to have 3 weeks, but 1 day shift to Tuesday. So the due date for the second programming assignment, I set it to Tuesday. Okay, so the same, you try, and it is an extension from the simple one to somewhat complicated one, the model, for example, the tandem model. And also I try to ask you to construct the confidence interval. Okay, so the same 3 problems for you. You guys can try. And if any question, you can send me the email, or maybe right now I have the email for the tutor. You can try to contact tutor to have some discussion with you if you prefer to have the discussion with our tutor. All right, that's all. Any question? If no, that's it, and see you next week. Bye-bye.